there won't be a talk today, tomorrow at 9:30, which was called, says TBA on the website. So the first talk will be Frank's talk at 11, and we'll have a group photo in between the 2 afternoon talks. So, okay, so tomorrow we start at 11. And now we have the first of Gabriel Dospinescu's lectures on p-adic Hodge theory.
Thank you. So I would like to thank the organizers for the invitation to give these 2 lectures here. They are very highly dependent on what Jared explained and will explain tomorrow. So we're trying to combine our courses so that we can give a broader overview of the theory of p-adic Galois representations. So I will be more concerned with the more analytic aspects of the theory, which is the theory of Phi-gamma modules, which was developed by Fontaine and then generalized and, let's say, enriched by the work of Colmez, Berger, Galois, and many other people. So Jared will try to explain more the geometric and the p-adic aspects, I mean, from the point of view of p-adic Hodge theory, and I will insist more on the interplay between p-adic Hodge theory and Phi-gamma modules. And so first of all, I would like to start by explaining why we use Phi-gamma modules. What are they good for? Well, for many people outside the field, one of the main reasons to use étale Phi-gamma modules is to write very long and technical papers that nobody understands because there are infinitely many rings, actually even uncountably many if you want, even though you can always create only countably many, which are enough. Of course, there are other applications of that. Well, in the title you see p-adic Hodge theory and étale Phi-gamma modules, so there are 2 different at first sight theories, and they are really different because p-adic Hodge theory deals only with certain specific classes of p-adic Galois representations. So Jared mentioned, for instance, p-adic Tate modules of a billion varieties or things like this. He will introduce other classes of p-adic Galois representations tomorrow, which he will call crystalline or de Rham or things like this. But they do not cover at all the whole class of p-adic Galois representations. So Fontaine introduced some amazing objects of semi-linear objects which classify all the p-adic Galois representations. Now you might think, why am I interested in all p-adic Galois representations? I'm only interested in those coming from geometry, let's say, and those are in the framework of p-adic Hodge theory. Well, the problem is that recent years show that it's very important to work with families of p-adic Galois representations. And in a family, you cannot hope to have all specializations to be, let's say, de Rham or crystalline. Of course, you can always create some subspaces inside the deformation ring so that this happens, but this is not the topic here. And also, recent work on the p-adic local Langlands program shows that it's very crucial to know, to deal with all the p-adic Galois representations and not only de Rham, let's say. And étale Phi-gamma modules are good for that because they classify all p-adic Galois representations, while some of the period rings that Jared will introduce tomorrow and study will only classify certain subsets of these representations. So let me make all this a little bit more precise. Let's start with k over qp finite. So the theory actually works in a much more general setting, but I will stick to this case. And actually tomorrow I will only take k equals qp to make notation a bit easier. And as usual, we fix some algebraic closure, k bar, and we denote by gk the Galois group of k bar over k, so the absolute Galois group of k. And we saw that, well, Jared explained that it's very important to think of this group as an extension of some rather, let's say, easy group downstairs by some complicated group here, but which can be identified with the absolute Galois group of some characteristic P field. So this is HK, which by definition is the Galois group of k bar over k infinity. And we saw in Jared's talk that by some amazing theorem of Fontaine, Fontaine, Berger, this is the same as the absolute Galois group of some characteristic P field actually complete discrete valuation field called the field of norms, and which is canonically attached to this infinite extension k infinity over k here. And I will denote the quotient gamma k. So this is the gamma from et al. Phi-gamma modules. Now, it turns out that you can actually develop the theory in the general setup that Jared explains, in which you can just take some tower of cyclic, totally ramified extensions, but I will just stick to the cyclotomic case, which is already very interesting. So from now on, I will simply choose k infinity to be k, and I add the p power roots of unity inside k bar. And then the action of the Galois group on roots of unity gives rise to this cyclotomic character chi. Well, it's not an injection here. And so this is the cyclotomic character. And this induces a bijection between gamma k and some open subgroup of Zp star. Right? So this gamma k here is some very nice group. Of course, if you chose some different extension here, gamma k could be more complicated. All right, so the point is that we're going to forget for a moment about representations of GK. We're trying to classify all representations of this group on finite dimensional QP vector spaces, and of course the action should be continuous. But we're going to forget about this group and focus more on this group here, HK. Now this group is the same as this one. So I will just forget about the field of norms theory, pick some random characteristic P field, but not perfect, and try to classify representations of GE. Right? So let E be any field. It's actually crucial to assume that E is not perfect because Jared explained that this is essentially some finite field, and then you take Laurent series in one variable over that field. So any field of characteristic P. Of course, in our case, we are interested in EK. So we want to classify QP representations of G sub E. Well, because GE is compact, any such representation will have a stable lattice. So it's enough to understand ZP representations. Right? And now, every time you have something over ZP, you can reduce it mod P, and you get an FP representation. And then you try, first of all, to classify FP representations of G sub E, and then to lift the whole theory and classify ZP representations. So for FP representations, things are quite simple. So FP representations of G sub E. Well, let's start with V, such an object. And let's consider the following object. I take the separable closure of E inside the fixed algebraic closure, and I tensor over FP with V. Well, as in Jared's talk, we have now a non-trivial Galois action on this guy, and we also have a Galois action on this guy. So there is a diagonal action now of the group GE on this, right? Specifically, G of x times V, tensor V, is G of x times, tensor G of V. Right? You should think of this E sep as being C in Jared's lecture, and V is, of course, the Galois representation that we're interested in. And now I can take invariance, and I will call the corresponding object D of V. Right, so what are the properties of this guy? Well, first of all, it's clearly an E vector space, right? Because E is fixed by GE inside E sep. And there is a natural map, which I will call phi from D of V to D of V, which is simply the map x tensor V goes to x to the P tensor V. Of course, you should think of this x goes x to the P as absolute Frobenius on the separable closure. And it's easy to see that this map commutes with the Galois action, so it really induces a map at the level of invariance here. Right? And of course, this map is not E-linear, but rather semi-linear. More precisely, if I look at phi of lambda x, well, lambda d is lambda to the p of d. That's clear on the definition. So you can think of this semi-linear map as being some map from, well, I take the tensor product of E over itself, but via the absolute Frobenius, and I tensor with D of V, and I go to D of V. And that is an E linear map. And now I make two claims. First of all, that this vector space here is finite dimensional, which is not a priori clear, over E, of course, and that the linearization of this map, which is exactly this linear map from here, is an isomorphism. So they both follow from the following fact. If I take E sep and I tensor over E with D of V, I go to E sep tensor over Fp with V, and the map is simply induced by multiplication inside E sep, I claim that this is an isomorphism. Well, why? If you think a little bit, this is just étale descent. Or if you want, the Hilbert-90 theorem. Right? We have an E sep tensor V. This is a finite dimensional E sep vector space endowed with a semi-linear action of GE, which is continuous, so it is generated by its invariants. There is a basis consisting of invariant elements, and this is exactly saying that this map here is an isomorphism. But this obviously implies, on the one hand, that this is finite dimensional, because on the right-hand side you have finite dimensional things over E sep, and it also immediately implies that the linearization of Frobenius is an isomorphism, because you can check this after extending scalars to the separable closure, and then it's clear. So this implies that, so this is the crucial result here, that this comparison map is an isomorphism, and this implies on the one hand that the dimension over E of D of V is finite, and this map here is an isomorphism. So now we can define our objects. So definition, I will let phi et al. Of E be the category of finite dimensional E vector spaces, D, plus a linear map from this E tensor over itself by the Frobenius, D into D, E linear isomorphism. In other words, you have finite dimensional E vector space endowed with an additive and Frobenius semi-linear map, semi-linear in the sense of the first line there. And the corresponding linearization is an isomorphism. And this is called the category of et al. Phi modules over E. And so this is very familiar for if when E is a perfect field, you get what we call isocrystals. Right? Okay. So we are going to talk more about isocrystals tomorrow and then make the link between isocrystals and all these et al. Phi modules via some rather deep theorems of Berger and Galois. Okay, so now we have the first theorem. I don't know who is the author of this theorem, so I'm not going to say anything about this. This seems to be a very classical result, namely that FP representations of GE is equivalent to phi et al. Of E. And of course, the functor is given by V goes to D of V. Of course, it's clear that this is a functor. It should be rather clear that the functor is fully faithful from this comparison isomorphism, because you can recover the Galois representation from this isomorphism here. Let me explain how. This comparison isomorphism is compatible with anything you like. So I can take invariants under Frobenius here. So what do I get? E sep tensor V phi equals 1, well, this is isomorphic to E sep tensor, wow. Tensored with D of V phi equals 1. But what is this one here? Well, this is exactly V. Right? So this shows that you can recover V from D of V, and so the functor is fully faithful. And it also gives you the hint for the quasi-inverse functor. You just take D and you map it to V of D, which is E sep tensor D over E phi equals 1. So in other words, if you want to get a Galois representation from an étal phi module, you have to solve a bunch of equations of the form phi of x equals x in some finite dimensional E sep vector space. Well, of course, it's not obvious that this is really a quasi-inverse, right? But what I showed is that if I take V and I apply it to D of V, this is naturally isomorphic to V. And of course, you have to prove also that if I take D of V of D, I get D. And this is not clear because it's not even clear that this is non-zero, first of all. Right? But you can check that this is non-zero and it has the correct dimension, and you also have an analog of this comparison isomorphism, and then that gives you the theorem. So this is a very classical but very important theorem. And now let's see how you can lift this in characteristic 0 when you have ZP coefficients instead of FP. Well, there you have to make some choice. The problem is that I said that this ring E is not perfect, or this field. So you cannot just lift E to, well, I mean, you could lift it to a ring of Witt vectors with coefficients in E, but that's a very ugly ring when E is not perfect. So what you have to do is to choose some complete discrete valuation ring in characteristic 0, which is absolutely unramified and having residue field E. Such a ring is called a Cohen ring for E. So pick a Cohen ring. So for the ones that I'm interested in, I will give you explicitly such a guy. So if you don't know what a Cohen ring is, just forget about it. You will have an explicit one in a few moments. Cohen ring for E. Call it OE. And lift Frobenius, x goes to x to the p, to some map phi from OE to itself. This is always possible by commutative algebra arguments, but of course this is not a canonical choice here. You have to make some choice. And now let's take A. Well, I take the strict tensalization of OE, and well, this turns out to be some discrete valuation ring. I can complete that. And this will be a Cohen ring for the separable closure. So far, so good. So now we have this A, and this Frobenius on OE is going to extend by general properties of strict tensilizations, is going to extend to a Frobenius on A. And we can compute the invariance under Frobenius, and we just get ZP. And now you do the same game, but you replace your ring E sep here with this ring A, and you replace E, where is it, this one, with OE. No. And you get the corresponding theorem, which works for ZP representations. And of course, the proof is just successive approximations, reducing in the end to the theorem in characteristic P. Of course, you have to work a little bit to make that statement precise, but this is not a very difficult result. So theorem due to Fontaine. The functors, well, I will say which one induce an equivalent. The functors below induce an equivalence. So I forgot to mention this equivalence of categories for FP coefficients is compatible with everything you want, with tensor products, with duals. So it's really very nice. And the functors are exact. Everything is fine. An equivalence between ZP representations of G sub E and étale phi modules over OE, where I can leave the definition of an étale phi module over OE as an exercise. So of course, these are finitely generated modules over this one, endowed with a Frobenius semi-linear map, whose linearization is an isomorphism. So same definition as for phi étale of E. And what are the functors? Well, V goes to D of V. So as I said, this E sep now becomes A. I have to tensor with V over ZP, and I take invariance. And conversely, if I have D, I take V of D. Well, I tensor with A, but this time over OE, and I solve the equation phi equals 1. So I forgot to mention that on this guy here, you also have an action of G sub E. Where does it come from? Well, the point is that the residue field of A is the separable closure. You have an action of G sub E on that, and you can lift it to A, again by properties of strict tensorialization. So from the action of G sub E on E sep, which is A over P. All right, so this is Fontaine's equivalence now. And you see that in this way, we classified representations of the absolute Galois group of K infinity, because I can just take E equals E sub K, and then GEK is GK infinity. So let me make a remark, because this is going to be useful later on. When you prove this theorem of Fontaine, as I said, you have to do some dévissage argument, some reduction to the mod P case. Well, if you want to make that work, you need some vanishing of cohomologies. So implicit in the statement of this theorem, in the proof, no, actually in the proof, not in the statement, in the proof of Fontaine's theorem, we also get that the age I of GE with coefficients A tensor V is 0 when I is at least 1. Of course, you can also prove this independently just by successive approximations again and reducing in the end to the case of FP representations when this is just Hilbert-90 theorem. So that's one point. And the fact that the Artin-Schreier exact sequence at the level of E sep, so 0 FP, E sep, 1 minus Frobenius, E sep, 0, lifts to some exact sequence in characteristic P, in characteristic 0. And this is very useful if you want to compute the cohomology of V in terms of the étale phi module corresponding to the representation. Because what you have to do is just tensor with V and take invariance. So if you do that, you will get the exact sequence H0 GE V goes to D of V goes to D of V. Here you have 1 minus Frobenius, and then goes to H1 of G sub E V. And then it goes to 0 by the long exact sequence in cohomology, because when you tensor with when you tensor with V, all these cohomology groups here are 0. So in the long exact sequence, you only get zeros at the end. And that gives you this exact sequence, which tells you how you can compute the cohomology. But if you want the invariance, you just take D of V and you solve phi equals 1. If you want to compute H1, you take the co-kernel of 1 minus Frobenius. So in other words, there is a very simple complex which computes the cohomology of a GE representation in terms of the étal phi module corresponding to that representation. All right, so well, as I said at some moment, if you want to pass from FP representations to ZP representations, you have to make a choice. And this choice is this one, the choice of a Cohen ring for E. So this is a rather serious problem if you start with any extension k infinity over k in the beginning, because you have to construct some canonical Cohen rings for these imperfect norm fields. And that can be quite hard. But in the cyclotomic case, there are some canonical choices for these Cohen rings, which make the theory work, because now you want to classify GK representations, right? So you need to carry on the action of GK in all these places. So it would be very nice if you had an action of GK on A, for instance, so that then you get a residual action of the quotient gamma k on the étal phi module. If you don't have such an action on A, then you will have some problem going from representations of GK infinity to representations of GK. So to classify GK representations instead of GK infinity, which is GEK representations, you need to choose OE so that there exists an action of the Galois group GK and not only GK infinity on A, which commutes with the action of Frobenius. Because if you manage to do so, then you can formally deduce from that theorem the exact same theorem with representations of GK on the one side and étal Phi-gamma modules on the other side. So let's assume that such a thing exists for a moment. And let me state Fontaine's theorem, which is really the classification theorem for Galois representations. So tomorrow, when we discuss overconvergence and Phi-gamma modules over analytic rings, we will see that it's very useful to have a more refined version of Fontaine's theorem. But for now, I'm going to stick to the historical statement, which is also very useful in practice anyway. So theorem, and this is Fontaine's equivalence of categories. Well, it says that ZP representations of G sub k are equivalent to étal Phi-gamma modules, gamma k modules, over, so now this is our first ring. I will call it A sub k. So every time you see sub k in many of these rings, and there are infinitely many of them, it means that we have to take invariance under the Galois group of k infinity at some moment. So you see, you always have some very, very big period rings, which carries no k. And then you add some subscripts k to denote that you took invariance. So this is a invariance under hk. So I recall that this is gk infinity. Right? And this will be a Cohen ring for our imperfect norm field E sub k. So this will be something like the Witt vectors of E sub k, except that this is not useful because E sub k is not perfect. And of course, the equivalence is as usual. So functors as before. Exactly the same formula here makes sense in this case, namely V goes to A tensor V, and you take invariance under GK infinity. And now you have an action of the whole Galois group on A tensor V, so you have an action of the quotient, gamma k, on the invariance under GK infinity. Okay, but I didn't tell you what are étal phi gamma k modules over AK. Well, if I said only étal phi modules over AK, this would be exactly the same definition with OE equal to AK. Right? So these guys here are étal phi modules over AK plus a continuous. So I do not want to discuss topology here because this is a nightmare for these period rings. So there is a certain topology on this guy, which is not the p-adic topology, so that it makes sense to talk about continuous actions of a group, plus continuous gamma k action commuting with Frobenius. All right. And now I have to tell you, how do we construct this object? So I have to construct this OE in a smart way so that I get an action of GK on A, and I have to tell you what this ring AK looks like in some simple situations. So now I have to go back to Jared's lecture where he introduced many rings, and we have to use those rings. So what did he introduce in his lecture? Well, he introduced some guy E tilde plus K, and he introduced some E plus K. So this plus means that this is the ring of integers in some field. And from this, he took fraction field, and he got some E tilde K. He took fraction field here, and he got the imperfect norm ring or field, which sits inside the perfect one. And of course, since they have a subscript, that means that there is some universal guy such that this is obtained by taking invariance. And of course, there is such a guy, namely E tilde plus. I can do exactly what he did, except that I work with C instead of K infinity. Right? And it turns out that indeed, if you take E tilde plus and then you take H sub K invariance, you get exactly E tilde plus K, even though this is not obvious, because it comes down to showing that, for instance, CP, where C invariant under HK is K infinity hat. After some mumbo jumbo with these definitions, it all comes down to this equality, which is the Axen-Tate theorem. You see, the problem is that you are taking invariance inside the completion of QP bar, and it's not clear that this commutes with the completion. That the invariance of the completion is the completion of the invariance. This is what this equality here says. So, yeah, now we have this very big guy, E tilde plus, which comes with an action of GQP. And of course, it has the absolute Frobenius on it because it's a ring of characteristic P, which is perfect. And so we can construct A tilde plus the ring of Witt vectors with coefficients in E tilde plus. And since this guy is a perfect ring of characteristic P, this ring is nice. And also Frobenius extends to an action of Frobenius on A tilde plus by functoriality of Witt vectors, and you also get an action of GQP on A tilde plus. And of course, you can imagine that you also define rings like A tilde by taking Witt vectors with coefficients in A tilde. Then you can amuse yourself and put subscripts by taking invariance. And there's a lot of decorations that you can put on these rings, and they all give you some highly complicated rings in characteristic 0. But remember that I want to construct A, which is not a perfect guy. Every time you see a tilde, it means that this guy is perfect in some sense, or obtained by completing the perfection of something. Okay, so what can we do? Well, recall that there was this element, T, which was the Teichmüller of epsilon minus 1, where epsilon was this funny guy, 1 zeta p squared and so on, which lived in E tilde plus. And the action of Galois on this guy is very simple, as well as the action of Frobenius. So essentially, by definition, the action of Frobenius on T is very simple, right? This is Teichmüller of epsilon to the p minus 1, which is just 1 plus t to the p minus 1. And the same, you can play the same game with the action of the Galois group. And you will see that g of t is 1 plus t to chi. I recall that chi is the cyclotomic character, chi of g minus 1. Good. So now we have this guy T, which lives in this very big ring, A tilde plus, but it actually lives in a much smaller ring, namely A tilde plus QP, right, obtained by taking invariance, because the Galois group of QP infinity acts trivially on T, simply because by definition, G QP infinity is simply the kernel of chi. Okay, now I can finally define the only Cohen ring which I can give you explicitly, and this is the one that I'm going to use tomorrow. So this is just, you take infinite in both directions series of the form sum of a n t to the n, where a n is in Zp, and a n goes to 0 p-adically when n goes to negative infinity. So this is a Cohen ring for, well, the reduction mod p, which is just fp double parenthesis t, and recall that this is just EQP. The imperfect field of norms for the simplest extension of QP, which is just QP. So you see that our Phi-gamma modules will be actually modules over this guy. Well, there is something not clear here in the definition. It's not clear how to actually make this series convergent, because you see a n goes to 0 p-adically only when n goes to negative infinity. So there is a certain topology on A tilde, which I'm not going to describe, so that you can make all these series convergent inside A tilde, and this guy here will actually live inside A tilde. So if all these rings get you crazy at some moment, and normally if you see this the first time, this is the normal reaction, you can just forget everything I said so far. The only point which matters is that we have an equivalence between ZP representations of GE and Phi-gamma modules over this very specific ring. And that's it. Right? Of course, this is only if you are interested about representations of GQP. If you have a finite extension, then you should construct analogous rings of this form, but then the actions of Frobenius and gamma will be very, very complicated. They will not at all be given by simple formulas like that. Okay, so as I said, this lives inside A tilde, but because you reinforced the well, I mean, you made it weaker, I guess. I never know what is weaker or stronger in topology. So there was a topology on A tilde so that this guy lives inside A tilde. And now, of course, you just define A to be the strict Henselization of AQP and then complete, and that will still live inside A tilde. So in some sense, this is the big guy in the theory of Phi-gamma modules. All the period rings that we constructed so far live inside this very, very big ring. Right? But this is just too big in some sense, so what you have to do is this is a perfect guy. So you would like to classify Galois representations in terms of étale phi modules over simple rings. You could actually use rings like that, but this would be very complicated because they are very, very complicated rings. And also, you want to do differential calculus, so it's very hard to work with differentials when you have perfect or completed perfections of rings. So that's why it's crucial at some moment to descend from these perfect guys to the imperfect ones. But as you can notice, there is a certain choice here. There is the choice of a compatible sequence of roots of unity. In other words, there is the choice of this epsilon. But this is not really important. Okay, so all this is very abstract. The question is, if I give you a specific Galois representation, even I have to say what that means, because usually I cannot give you a Galois representation by specifying matrices of the action of an element of the Galois group. But let's say if I give you a certain Galois representation, how do I compute the étale Phi-gamma module? Well, of course, I go back to the definition, and I try to tensor with this huge ring A, and then take invariance, and of course, that's very hard. So there are a certain number of big theorems which allow you to compute the étale Phi-gamma module, but I should emphasize that the purpose is not actually to write down the matrices of Frobenius and gamma here, because I will give you an example. Even in the case of an elliptic curve with ordinary reduction, the matrices are a total mess, and you cannot understand anything from those expressions because they are just too complicated. But the point is that in some sense here you have objects which are easier to compute with. At least you can write down matrices of the Frobenius and gamma, and you can try to do some differential calculus. We're going to see tomorrow that if you replace this ring AQP, where is it? This one, with some ring of convergent power series or certain annuli, then things become a lot nicer because those series will actually converge, while if you take a series here, it doesn't converge anywhere. But this will already be a big and hard theorem in the theory. So, of course, tomorrow we're going to see in practice how do you match this theory of étale Phi-gamma modules and p-adic Hodge theory. For instance, if I give you an elliptic curve, let's say, and I know it's crystalline cohomology, then probably there are some big theorems in p-adic Hodge theory which allow me to compute the decrease of that. God knows what that is. There will be a certain isocrystal which is canonically attached to my representation. And the question is, how do I construct the étale Phi-gamma module knowing that information? So that will be the subject for tomorrow. But now I would like to give you an explicit example of étale Phi-gamma module. But before doing that, let me come back a little bit to the computation of cohomology. So we saw that it's pretty easy to compute the Galois cohomology of an HK representation. You just look at the kernel and co-kernel of this 1 minus Frobenius. Now, it turns out that you can do the same with GK representations, but of course, the complex becomes a little bit more complicated because you also have the action of this gamma group. So let me tell you how do you do it. Well, let's try to compute H0 of GK V. Right? Well, of course, this is H0 of gamma K, and then I take H0 of HKV. Right? I'm just saying that taking invariance, I can take first under HK, and then I take under the quotient. And this is H0 of gamma K. And I already computed this one. This was D of V Frobenius equals 1. And now the point is that, as I said in the beginning, this gamma K is an open subgroup of ZP star. So, well, at least if P is bigger than 2 or 3 or I don't know what, this will be some procyclic group. So it's very easy to compute such cohomology. You just compute Frobenius invariance, and then you mod out by gamma minus 1, where gamma is a topological generator of gamma K. Well, if gamma K is not procyclic, you just have to mod out by its torsion subgroup, and then the formulas become a little bit more complicated. Right, so this shows how you compute H0, which is not always the most interesting one. Now, how do you compute H2? Where is it? Well, here you use this kind of idea. First, you take cohomology of HK, and then you have to deal with cohomology of gamma K. So, as Frank explained in the morning, there are some spectral sequences. In this case, there will be an Hochschild spectral sequence for the cohomology. And if you combine that with the remark that I made about the cohomology of A tensor V, that will give you in the end that H2 of GKV is the same as H, I always forget, H1 of gamma k into, oh, but I said nonsense here. This is, of course, invariant under gamma k, right? This is an H0, not an H1. Now it's an H1, and now we take co-invariance. So gamma k into H1 of HKV, right? And this was, what was H1 of HKV? Well, this was d of v over Frobenius minus 1. And now I take co-invariance under the action of gamma k. So this is d of v over phi minus 1 gamma minus 1. Now, H1 is a bit more complicated to compute using this kind of thing, even though the final formula is very simple. Actually, there is a very simple complex, which I will write down now. So here I send x to Frobenius minus 1x, gamma minus 1x. And here I send xy, I guess, to phi minus 1 x minus gamma minus 1y, or the other one if I didn't match them correctly. And it turns out that the cohomology of this complex is the cohomology of my representation. Well, you may argue that this complex depends on the choice of my topological generator gamma for this procyclic group gamma k, but you can actually renormalize everything so that this disappears. And in practice, you don't care because you just take one topological generator and you compute cohomology with that. So that's a very nice theorem of Fontaine and Herr, that the cohomology of gk, the coefficients in V, is the same as the cohomology of this complex. Right? This will be the complex C of D. So that tells you that, for instance, if you want to compute H1, you have to solve equations of the form Frobenius minus 1x is gamma minus 1y. Et al. Phi-gamma module, which can actually be quite complicated if you work with a very specific one, but at least it's a way to compute cohomology for Galois representations. And actually, I should say that I cheated a little bit because I used the full power of everything we know about Galois cohomology of p-adic fields, which is, of course, due to Tate and so on. So there are a bunch of big theorems that I used here, including finiteness properties and things like this. But when he proved this theorem, Herr actually started from scratch. He just used the theory of et al. Phi-gamma modules to prove this theorem, and then he used the theorem to reprove all the big theorems that Tate proved about Galois cohomology of p-adic fields. So this is very interesting. This already shows that you can prove non-trivial results by using Phi-gamma modules and go back and get information about Galois representations. Of course, this is not very surprising because you have an equivalence of categories. But in practice, it can be quite hard to write explicitly what this means. So yeah, I cheated a little bit because if you want to prove this theorem without using all the big theorems about Galois cohomology, of course, the proof is a lot more difficult. Okay, so I would like to end this lecture with an explicit example of Phi-gamma module. Well, actually, two explicit examples. So let me start with the easiest one. Let's take a character of GQP. So I should say that if I replace QP here with other guy, any other field, things become a lot more complicated. It's quite hard to write down explicitly the et al. Phi-gamma module with the action of Frobenius and gamma if this ring here is not QP and its other field. And the point is that you have to understand at some moment the relationship between local class field theory and the field of norms, and this is not obvious at all. So let's take such a character. Well, we know by local class field theory that this corresponds to some character, some unitary character from QP star into ZP star, which I will denote by the same letter. And I would like to understand what is D of ZP of delta, where this is obviously the, the free, this is ZP times E, where G of E is delta of G times E. Right? So I have one-dimensional representation, well, free rank 1, and I would like to compute the étale Phi-gamma module of that. And it's a very good exercise for you to check that this is just, well, you take AQP, so this was the power series ring before, and you twist it by delta, and I have to tell you what that means. So as an AQP module, this is just AQP. So it will have some basis x. And now I have to tell you what is Frobenius. Well, the Frobenius on x is delta of p times x. And you can guess that gamma of x is delta of chi of gamma times x. So this is very explicit and very nice. But you already see the interplay between étale Phi-gamma modules and local class field theory. And by the way, another very good exercise is to try to understand abelian representations of GK in terms of étale Phi-gamma modules. Again, when K is not QP, things get complicated. But when K is QP, there is a very explicit way to write down the étale Phi-gamma module of an abelian representation. Actually, already for an unramified representation, this is interesting. Okay. And now let's go back to Jared's first example, namely E over QP with good reduction, an elliptic curve with good ordinary reduction. Right? And I would like to understand, so I let V TP of E, p-adic Tate module. So this is a free ZP module of rank 2 with a Galois representation. Jared explained that this is actually reducible in this case because I assume that we have split, we have good ordinary reduction. So this V will sit in some exact sequence of this form, chi delta inverse V ZP of delta 0, where delta will be some unramified character. Of GQP, which corresponds by that correspondence between characters of GQP and characters of QP star to some character delta, which is simply alpha to minus VP of x for some alpha in ZP star. Right? Because the character is unramified, it has to be trivial on ZP star. So, of course, since the functor V goes to D of E is exact, I can apply the functor to that exact sequence, and I will get that I have an exact sequence of the form AQP of chi delta inverse D of V, AQP of delta 0, where these are the étale Phi-gamma modules of rank 1, which are defined here. Good, so now I need to understand this extension. Of course, I may assume that the extension is not split because otherwise the problem is not interesting. I already know these two guys here. So suppose non-split. Well, it's an easy exercise using Tate's result on Galois cohomology to see that there is only one non-split exact sequence of this form. So if I can give you the étale Phi-gamma module for one single such extension, I win. That will be my D of V. How do you construct that? Well, as I said, now you have extensions. Extensions are related to Galois cohomology. Galois cohomology is computed by some complex which is gone, by Her's complex in terms of Phi-gamma module. That comes down to solving some equations. And here I will write down explicitly what the equation is. You need to solve this equation. Alpha squared phi minus 1x is chi of gamma, gamma minus 1, y, with x and y in AQP. So I will spare you the easy and straightforward reduction to this. So you want to solve this. Okay, now let me make a choice. I will give you one solution of this equation. And of course, you have to make sure that y is not in the image of this, because otherwise your extension is split. So you cannot just take anything there and construct the corresponding solution, because when computing H1, you had the quotient between the set of solutions of this equation and the certain image of this one and this one. So you need to solve this equation such that y is not in the image of that. Well, let me give you an example. Take y to be 1 over t plus 1 over 2. So I will assume that p is greater than 2. This is an AQP. And it's an excellent exercise for you to check that chi of gamma, gamma minus 1 of y lives in t times a plus qp. And what is this guy? Well, this is t zp double bracket t. So there are no denominators. In general, guys in AQP have infinite denominators in t. Here there are no denominators, and the constant term is 0. I'm finishing in 1 minute. Okay. And now it's very easy to solve an equation of the form 1 minus alpha squared Frobenius x. Sorry for slightly changing the sign there. How do you solve this equation? Well, you formally invert this one. You just write x as 1 over 1 minus alpha squared phi of 1 minus alpha squared phi x. Right? This doesn't make any sense, but I'm just trying to motivate how you do it. You expand in power series that one. So this is the sum of alpha to 2n phi to the n. And this one is given by this explicit expression. And here's the miracle now. Since you made your y so that this guy inside vanishes at 0, that sum converges in AQP. It even converges in this ring, right, for the p-adic topology. And that's it. You got a solution x, which is this very complicated power series in AQP, right? And you had a very simple y, and that gives you a solution. And of course, there is a very good exercise for you to check that this y is not in the image of this operator, which is not that obvious, actually, because you have to solve equations in this very big ring. All in all, what you get is that if you look at D of V, you can find a basis in which the matrix will look like that. The matrix, yes? So the matrix of Frobenius in a certain basis will be alpha, 1 over alpha, 1 over t plus 1 over 2, 0, 1 over alpha. And then you will have the matrix of gamma, which will be chi of gamma. But of course, the diagonal terms are not surprising at all, right? We have an extension of 2 already known guys. The point is what you put here. And here you put this very complicated guy. And here you put 0, and then you put 1. So the upshot of this is that in general, the matrices of Frobenius and gamma will be highly complicated. Tomorrow, we're going to see the case of elliptic curves, of supersingular elliptic curves, and then the expressions will be even more complicated. But the point is that you can actually write down from time to time such a thing. Of course, this would completely break down for a supersingular elliptic curve, because in that case, the Galois representation is irreducible, and there's no way you can do Galois cohomology. So this will be a lot harder. We will see that first we have to compute decrease of that, a certain filtered isocrystal, and then there will be a highly non-trivial theorem of Berger, which allows you to construct the Phi-gamma module from that. Okay, sorry for going more than